Welcome back, BC folks. I hope everybody's doing well. We're going to learn the last two of the 10 tests, and then I also have on your last page of today's notes a summary sheet, and we'll kind of use that to wrap things up. I think you're going to like the ones today. In fact, this one is a very powerful one, the ratio test. Before we did a limit test, and we were comparing the limits of two known series. Misspoke there. Series. Now we're comparing as a limit. We're taking a limit here, but we're comparing the next term divided by the current term. Okay? So if the next term divided by the current term is going to be less than 1 as we take that limit, then that series is going to converge. If we take the next term divided by our current term and that's greater than 1, and it diverges, and it's inconclusive, so you'd have to find another test if it's equal to 1. All right, so I think you'll see these as we go. They're pretty cool, and a good question that's come up in office hours and in years past is how do we know which one to use? This is definitely a good test when you've got factorials and exponential functions. So think of this one. So a sub n is just 2 to the n, over n factorial. A sub n plus 1 is going to be, wherever you see an n, plug in a n plus 1, 2 to the n plus 1 over n plus 1 factorial. Now, it definitely matters. Before, remember I said it didn't matter if we were comparing those with the limit comparison test. You'd either have 3 or 1/3, the top or bottom order didn't matter for numerator and denominator. Here it definitely matters. So we need to always take the limit as n approaches infinity of a sub n plus 1 over a sub n. Well, a sub n plus 1, and need the limit definition here, of 2 to the n plus 1 over n plus 1 factorial divided by 2 to the n over n factorial, the original sequence that we're looking at. Okay? Our series, I keep saying sequence, original series. So we're going to have a very ugly looking 4-decker fraction here. You'll probably always do this from now on. Just go ahead and flip and multiply your original series by times the n plus 1 series. So we're going to rewrite this before we try to get too clever. Limit as n approaches infinity to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. Okay? Now, next time when we go ahead and flip that other one, you might even want to organize your thoughts, but aren't I going to compare the n factorial terms and the n factorial terms, and the 2 to the n and the 2 to the n? So I can simplify those. I hope you would all see this. Limit as n approaches infinity. 2 to the n plus 1 divided by 2 to the n. Well, back in Algebra 1, when we had x to the divided by x to the, we subtract the powers. So it's going to leave us 1, 2 on the top. And then n factorial over n plus 1 factorial. So think about what n factorial is. N minus 1, ... 3, 2, 1. N factorial, we'll just write this up here as a kind of an aside. N plus 1, right, is our last term. I'm starting with it because I'm building my way down. Times n minus 1, ... 3, 2, 1. Clearly the 3, 2, 1s are going to divide out. Okay? N minus 1 cancel out. N and n cancel out. We'd have n plus 1 on the bottom. You can all take that one, right? The limit as n approaches infinity of 2 over n plus 1 is equal to 0. Okay? And since the ratio of the next term divided by our current term, the limit of a sub n plus 1 over a sub n, and it is absolute value, so if we had a negative number there, it still clearly has to be a fraction, in other words. That is less than 1, so we're good to go and say, therefore, the series, and we're talking about this series here, 2 to the n over n factorial, the series converges by the ratio test. Always name your test that you're using. Okay, next one. A sub n plus 1. Well, wherever you see an n, we're going to plug in an n plus 1. So we've got that, right? n plus 1 equals n plus 1 squared. 3 to the what? Well, if I plug in n plus 1 for n, I'd have n plus 1 plus another 1. Wouldn't that be 3 to the n plus 2? Divided by 2 to the n plus 1. Okay, so I'm going to take the limit of that, and to be very literal, I should put absolute value there. That's going to come in handy later, so we'll go ahead and save ourselves some time. I forgot those, so I apologize. It is the absolute value. We mentioned it, but it's better just to go ahead and put those in there. Limit of a sub n plus 1 over a sub n, put that in there too, as n approaches infinity. Limit as n approaches infinity. I'm going to go ahead and write my a sub n plus 1 term. N plus 1 squared times 3 to the n plus 2 over 2 to the n plus 1. And I'm just going to do times because we're going to flip and multiply. We saw that before. B to the n, it was on the bottom, now it's on the top. N squared times 3 to the n plus 1. Now, be careful. Not everything's going to just simplify and cancel, but a lot of terms will, and that's what you're relying on. Okay? Well, let's see. Let's do each type first. So we got 3 to the n plus 2 over 3 to the n plus 1. 3 to the divided by 3 to the. We're going to subtract the exponents, and there's more of them on the top, so we'd have 3. Same idea here with our 2, right? We've got 2n here. And we'd have just a 2. Okay. And then what about our n plus 1? That's where we have to be careful. N plus 1 squared over n squared doesn't just cancel. Okay. So we have n squared here. That's cool. We have what on the top? Well, if I were to multiply that out, it'd be n squared plus 2n plus 1. And we could expand this one more time. Limit as n approaches infinity. 3n squared plus 6n plus 3 over 2n squared. That limit looks like one we should be able to do. Our degree of n is the same on the top and the bottom, so we're going to take the ratio. That equals 3/2. Therefore, right, even though my limit work is over here, we'll start this over here then. Therefore, the series what? Well, 3/2 is greater than 1, so the series diverges by the ratio test. Okay? This will be a very handy test for us, so don't throw this one away. I like this one. And those of us that are wondering on the condensed 2020 year of is it going to be on the AP test, this was a topic that they said could be tested. So I want to make sure that, and it's an easy one. Okay? It's an easy one. All right? A sub n plus 1, last one. Well, wherever I see an n, it's plus 1, so isn't that n plus 2 factorial? Over 3 to the n plus 1. So I'm going to take the limit as n approaches infinity of the absolute value, n plus 2 factorial, over 3 to the n plus 1, divided by, but we'll just flip and multiply, 3 to the n, and n plus 1 factorial. Limit as n approaches infinity. Well, the 3 should be easy, right? We've seen that now. That's 3, right, on the bottom. N plus 2 factorial, isn't that one more term than the n plus 1 factorial as we think about multiplying 1 times 2 times 3 times 7 times 8 times n plus 1 times n plus 2. So n plus 1 is going to divide out. N plus 2 will be all that lives. So we've got that. The limit as n approaches infinity of n plus 2 over 3. That's the easiest limit we've taken all year. That's infinity. Therefore, the series diverges by the ratio test. Okay, and again, an easy way to check that. So if I were highlighting my notes here, I would highlight works especially well when we have terms with factorials and exponential functions, and there you have it. Okay. All right, we'll learn later that those power series will also use that a lot because there'll be a lot of exponentials with those. All righty. The root test. We're up to test number 10. Isn't that great, right? The root test. This one is going to be easy to identify because if the series expression, you could take the root of it, if it's rootable. I don't know if that's a word, but you'll see what I mean. Here, if we've got the nth root of our expression, if we can take that limit there and it's less than 1, then the original series is going to also converge. If we can take the square root, or not necessarily square root, the nth root, sorry, of that. So we've got a bunch of n power kinds of things. The absolute value of that, the nth root of that is greater than 1, that the series is going to diverge. And it's, again, inconclusive. It's equal to 1. You'd have to find another test. Let's go ahead and write this one out. The limit as n approaches infinity. Well, I've got e to the 2n. I can take the nth root of that, and I've got n to the n. I certainly can take the nth root of that, so I'm going to put in a mega nth root here. Okay? The nth root of e to the 2n. Remember, that's just e to the 2n to the 1 over n power. Isn't that e squared? So the limit as n approaches infinity, e squared, over, what is the root, the nth root of n to the n? We're saying n to the n to the 1 over n power, right? When you have power of a power, you multiply the powers here, so the n and that n cancel out. All we have is n. E squared over n as n approaches infinity equals 0. E squared divided by a giant number is equal to 0. Therefore, our series is going to, that's the first example there, converge by the root test. These are maybe the easiest ones other than finding an alternating series, because if you can take the root, like, oh gosh, that's a root power. Oh, that's a power, that's a power. Okay, so if you've got a power, nth power thing, you can take the nth root of that. Well, let's go ahead and try it on this next one. Limit as n approaches infinity of 3n plus 4 over 2n to the nth, but I'm going to take the nth root of that, okay? That nth root and that nth power kind of divide each other, or not really divide, but power each other out. Limit as n approaches infinity, 3 to the n plus 4 over 2n. We all can take that limit, right? You got 3 and you got 2, or degrees are the same. You've got leading coefficients of 3/2. Therefore, our series, what? Well, it's greater than 1, diverges by the root test. Congratulations, we made it through all 10 tests. And you've learned a lot. And I bet this, if you are honest with yourself, this was a little different. This is something that we hadn't done. In fact, here they are. You've got this worksheet, so you don't have to copy this down, unless you're copying your notes, which would be a great idea too. This clearly was, I should attribute this to a textbook that we used to use for calculus. The first one, and I love these comments. We've got a series, an example, if it converges, if it diverges, and comments. The nth term test. That was a great one to start with because you've got some series a sub n from 1 to infinity. Not any information about the converging idea, but gosh, a wealth of information. It diverges if the limit as n approaches infinity of that nth term is not equal to 0. This test can only be used to show divergence. It cannot be used to show convergence. Make sure you keep that straight. Okay? Geometric series tests are going to come in this form, from n equals 0 to n infinity, or it could be 1 to infinity if they change up the power there. But a is your first term times r, your common ratio to the nth power. that geometric series will converge if R, the repeating number, the thing with the power, the common ratio, is the absolute value of that is less than 1. You're multiplying by 1/2 times another 1/2 times another 1/2. Each of those are going to get smaller, smaller, smaller. If the ratio is equal to or greater than 1, then you're getting bigger and bigger, bigger terms. How could it converge if those terms are getting bigger? An important one here that we're going to need in the next topic as well is the sum. The geometric sum equation is the first term A over 1 minus R, your common ratio. Telescoping series, that's when you condense it, like the telescoping of a tripod, like a camera stand. If it condenses down, you can take the limit. P series, when P is greater than 1, and again, it's come in this form, 1 over n to the P, not n to the negative P. It's 1 over n to the P. Those P series are going to converge only when P is greater than 1. So here we had R is greater than 1, it diverges, so yeah, details, yeah. But if you think about what's happening, it makes sense. And it diverges when P is less than 1. A special case when P is equal to 1 is called the harmonic series. Alternating series. And again, there were conditions with this, but the summary sheet is you've got a -1 to the n power and minus 1 power. Alternating series, that has to be decreasing, and all the terms are positive, right? It's greater than 0, but a sub n plus 1 is less than a sub n. Those terms are decreasing. And the limit of the a sub n is equal to 0. There is no divergence information because it would default to the nth term test if it did. Having a drink here of water. And let's see, our remainder. The remainder is the absolute value of the next term. Integral test, okay, and these are the conditions here. F had to be continuous, positive, and decreasing. You check those. If the integral converges, then its corresponding series would converge. If the integral diverges, its corresponding series would diverge. And the remainder, we talked about that there. Root and ratio, I think those were pretty straightforward. They're right here. Direct comparison, that's what we did the previous day. Direct comparison, if the bigger of the two series converges, then a sub n is going to be trapped by that as well, and a sub n would converge. Remember, we're always talking about a sub n here. If the bigger is the one that we're given is diverging, then the one that is the bigger one, right, is going to be pushed out by b sub n. We're always thinking about a sub n is the one we've got, b sub n is the one we're comparing it to. Okay, so again, if b sub n is holding it in, a sub n is going to converge. If b sub n is pushing it out, then a sub n is also going to have to diverge. And then the limit comparison test. And again, we did use limits on the root and ratio test today, but remember this one, we're comparing the limits of two series. If that limit of a comparable series is finite and greater than 0, then the which is greater than 0, then if the limit converges, the a sub n would converge. If the limit diverges, then the original series would diverge. This is all good stuff. Please start practicing. It gets really confusing when we throw them all together. So the next time we meet, I'll have a worksheet that kind of mixes it all together. But this is good stuff. So start practicing these and thinking about the conditions. Don't just get confused about what we're talking about. Break these apart, and if you understand what you're doing, these really aren't that bad. Have a great day, and I'll see you all next time.